Modern society depends on reliable electricity as an essential source for nearly all aspects of life. Consumers expect electricity to be available at the flick of a switch. While most have experienced local power outages due to storms or accidents, we do not expect a massive outage on a calm, warm day. Transmission lines, interconnected at switching stations and substations, form a network called a power grid. Electricity flows along the path of least resistance through the interconnected network of transmission lines from generators to loads. Ever-increasing demands have exposed the vulnerability of the grid. The Northeast blackout in August 2003 is an example of the grid's susceptibility to cascading failures. One failure in one location was propagated throughout the system by the cascading effect. One failure led to another until the majority of the Northeast was without power. Along with traditional problems of the inability to store electricity and control the path along which electricity flows, reliable operation of the power grid has become even more complex and demanding because of its excessive usage for modern technologies and hence overloading. This project set out to improve the robustness of the power grid against cascading failures through distributed wind and solar generation. The simulation has been tested for a 14-bus system representing a part of the power grid of the Midwestern United States and a 247-bus system representing a part of the power grid of New York State. From a networking point of view, we analyzed the grid as an interconnected network referring to the buses as nodes and transmission lines as links. The links and nodes are characterized by a finite capacity. Blue dots on the network represent the nodes. Loading of a link is represented by a change in color. A blue link highlighted by a red circle is a failed link. After removal of an indicated link, power capacity is redistributed among other links, offering the least impedance in the absence of the removed link. Even though the amount of power being transferred is now less, few of the links reach their maximum capacity of operation and fail, a phenomenon known as overloading of links. The animation shows the redistribution of power after each removal of overloaded links. Disconnected nodes, represented by red dots, are moved to their corresponding locations on the power grid. The power degradation graph on the bottom right shows the degradation in load-bearing capacity of the network as the links and the nodes are removed. These animations illustrate the cascading effect. Again, the removed link is blue and circled in red. This link is important because it carries a large amount of power. As this link fails, it overloads neighboring links, causing them to fail, in turn causing more links to fail. Nearly 100 nodes are disconnected before the system becomes stable again. Several mitigation strategies can be implemented to reduce cascading failures. An ideal solution would enable the entire network to return to normal operation without any losses or delays. The system would sense the failure and take action required to prevent further overloading and consequent failures. This mitigation strategy aims at reducing the large loads on a few key nodes. This will reduce the overall load on the system because of demand-supply characteristics of the network. It will also reduce the number of nodes disconnected from the system to some extent. However, intelligent selection of nodes for load reduction is the fundamental principle determining the success of this strategy. The power grid is a combination of cyber and physical components. Grid operation is controlled by circuit breakers, relays, etc., which are in turn controlled by computer software. State-of-the-art technology will aid in control and monitoring of effective communication and control systems, as well as control disturbances and identify the need for use of distributed sources.